Okay, am I mic'd? Can you hear me? Yeah? Yeah, okay, good. Let's mess with the lighting, shall we? That's better. So everybody, probably for the last time, hi. Look at the turnout today, like 10 people. All right. So something tells me the exam questions pertaining to this lecture are going to be particularly problematic. Am I that mean? Maybe. How many of you were at the epidemiology thing yesterday? Nobody. Interesting. You okay? You. Yeah. It's still on. Yeah. It's on YouTube. Yeah. So you can visit it if you care to. And you missed out on free beer as a thing. I didn't. That's why I'm rehydrating now because I'm struggling. Okay. So this is the last new thing that we're going to do in this class. You should be very, very sad, because you'll learn so much already. And next class we'll go over the semester, the half semester, and talk about the final, but this is the last thing. And what we're talking about is sample size calculation, which is one of the most important statistical tasks that we do in professional science, because we need to know how many people to have in our study, how many animals to have in our study, etc. There's a famous, not that famous, I guess, but every year, the Canadian Medical Association Journal, for their Christmas edition, publishes a particular issue that has questionable science. It's real science, it's just kind of wacky. So one year they published a study that attempted to show an association between your astrological sign and whether or not you'd win the Nobel Prize in medicine. And they discovered that, I think it was Libras are more likely to win the Nobel Prize in medicine. I made that up. It could have been Taurus. I don't know. So don't be too happy. Right? And what do you think the conclusion was? Because the analysis was real. They did the math. It was real. And they correctly made a conclusion. Can you guess what it was? Well, you probably couldn't guess what it was because you haven't had this lecture yet. But the conclusion was, with a large enough sample size, you can determine pretty much anything. You can have any answer you want. That's true. So it's possible to have an overpowered sample such that you find every possible association nuance. And so the finding is not real. It's kind of like, ever watch House MD? There's a lot of episodes, the other doctors will encourage him to put the patient under a full body scanner, and he always refuses. No, we won't do a full body scan because we'll always find something. If you find something, you have to address it. And very often, the something is not that important. If I put you under a scanner, you probably find, oh, one of your bones is misaligned, or you got something in some blood vessel somewhere. It doesn't mean anything. The same with overpowered sample. You're always going to find something. But that's not typically the problem with sample size issues. Typically, the problem is you haven't got enough people in your study to detect the thing that you're looking for. So today we're going to look at some of the issues theoretically around sample size determination, and then I'm going to show you two formulas for computing the sample size on very specific circumstances. And we've chosen those two formulas because they are easy. In real life, there's so many different factors involved that a sample size calculation can take days and many pages, and we often hire professionals to do it. There are websites you can go to that do sample size calculations, and very often we rely on them. They're just not really right, but we still rely on them. That's the nature of science today. We kind of cut corners and make mistakes. So my PhD thesis, I have an entire appendix, 12 pages, on my sample size calculation, and it's not fun. But we won't be doing that. You'll be doing just two very simple equations. That should be straightforward. Okay, so the slides that we're looking at here were stolen from my friend Nick Berriman, who was there last night. You could have met him last night, but no. He's a senior statistician at CHIO, and he gave a guest lecture in this class many years ago using these slides, and I've kept the slides. So we're going to go through an example here, and this example touches upon a lot of the stuff we've done throughout the year. I think it brings it together fairly well. The example is a pill that lowers blood pressure. Right, so let's say you scientists have invented a pill that we think lowers blood pressure. We're going to phrase a null hypothesis. We're going to talk about type 1 and type 2 error, things you've done already. We're going to look at the sampling distribution of the mean, things we've done already. We're going to and then talk about the factors that affect sample size, and we're going to compute sample size for two different types of groups. We're not doing this last thing. Take the last point out. Literature, who cares about that? Yeah. So here's an example. Physicians, doctors, scientists, whatever, design a pill, an intervention, that's going to reduce the blood pressure of people who have high blood pressure. All right, so they've done some case series. They've looked at a couple of their patients. They've given the pill. Oh, it fell. That's great. But we don't know if those are just flukes. We don't know if it'll work for everybody. Maybe they've done animal populations as well, but we don't know if it's going to be actually effective on the marketplace. So we have to do a study, right, to see if it actually works, if it's efficacious. These are efficacy studies. We need to know how many people to have in our study to determine if the pill works. Now, if you're going to design a study to test whether this pill works, how would you do it? Give me a vague idea of what the study would look like. Yes?
You give some people a pill and check their blood pressure over a period of time, and you don't give some people the pill and check their blood pressure.
Exactly right. Okay, so what you describe is a randomized control trial. We have two groups of people, some get the pill, some don't, and we see how much the blood pressure goes down in each group relatively. That would be a two-group design, but let's say I only looked at the ones who got the pill and I ignored the ones who didn't get the pill. That's a one-group design. So there are those are two different scenarios, and each scenario has a different sample size requirement. There's a whole other types of studies remember we talked about case controls and cohorts earlier. We could do that as well. But for this, we're only looking at randomized control trials and single control trials. So if we have too few people, we will not detect a change in blood pressure, even if there is one. So we'll fail to find the efficaciousness or the efficacy of this pill that may be changing lives. If you have too many, I mentioned it's possible to artificially detect things if you have too many, but more commonly, we're going to expose people to risk. Right? We want as few people as possible, such that not everyone has to undergo this. Also, it's costly, so we want to keep our costs down. So that's why sample size calculation is an important thing that drug companies in particular go through. Okay, so what will be the null hypothesis of this? Well, it's on the slide already, you see it. But the null hypothesis for this kind of test is going to be, of course, that there's nothing going on, that the pill does not change blood pressure, does not lower blood pressure. Right? So we can have the H7 and this is the burden of proof that we are trying to ascertain when we do our study. We're trying to find sufficient evidence to reject or fail to reject the null hypothesis. I mentioned when I talked about null hypothesis earlier in the semester that I always say we fail to reject, we never accept. But some statisticians feel differently. Nick is one of those that says accept. So on this slide, he actually uses the term accept the null. You don't do that. You fail to reject the null. You don't accept it. Okay. So obviously the people who are designing the study think that the null hypothesis is false. They are seeking to reject the null. They fully expect to reject the null. They do not expect to retain it or to fail to reject it. Right? So we're going to have a study that puts the null to the test. Now, there's a review of the type 1 and type 2 errors. So we have two possible outcomes of our trial, either that has no effect, the drug doesn't work, or the drug has an effect and it works. If it doesn't work, we fail to reject the null. We don't accept it. We fail to reject it. If it does work, we reject the null. You remember this, right? We also know that there are two possible realities, and that is either it works or it doesn't work. Sorry, it works or it doesn't work. It doesn't work, it works, right? So that, and you recall, this is how we get our type 1 and type 2 errors. So if it doesn't work and we fail to reject the null, that's great. If it does work and we reject the null, that's also great. But these two scenarios are bad. Remember, a type 1 error is when it works, but we fail to find that it works. And a type 1 error is when it doesn't work, but we think it does. And we also concluded in this class that this is probably the more serious concern. So remember we talked about, the trial, the murderer, and all that stuff. That's what we're talking about here. All right, so we tend to want to reduce this as much as possible. But there's a trade-off here. As one goes up, the other goes down. So let's remember all that. So this is an important consideration when we do our sample size calculation. Type 1 and type 2 error. Here's the study. So again, when we're doing this kind of study, we have an inferential population. Ultimately, we want this pill to be used for everybody who has high blood pressure, not just the people I recruit for my study. Okay, so we take a sample from everybody who's eligible, and we measure their baseline blood pressure, and we give them the pill, and we find out how much their blood pressure changes, right? So our outcome is the change in blood pressure. At this point, we have to think about how much of a change in blood pressure is important. Somebody's going to change by some amount anyway. You change your blood pressure by sitting down just now, or by having a cup of coffee. So there's so much perturbation in this already, so much noise in the system, that we have to figure out how much of a change is meaningful to us. That's the effect size. right? The effect size is one of those considerations that's going to affect how many people we recruit. A bigger effect size, well, what do you think? What's easier to detect, a big effect size or a small effect size? Bigger things, exactly. Bigger things are easier to see, as simple as that. Right? So, if I have a big effect size, I probably don't need as many people. I don't need as rigorous a study. If I have a small effect size, I need a really well-powered study and probably a really good study to detect small nuances. So keep that in mind. So the change in blood pressure that I want to detect would be determined by clinical knowledge. The people who invent the pill are supposedly experts on blood pressure. They would know what's a meaningful change. If it's only going to change like 1 millimeter of mercury, is that worthwhile spending millions of dollars on a pill? Probably not. If it's going to change like 10 or 15 or 20, that's probably worthwhile. So that's a clinical choice, an expertise kind of choice. Right? Now, the null hypothesis is going to be that the change is zero. There's no change at all. Now remember, we know that this is a statistical change. There's always some variation here. So maybe a change of like 1 or 2 is the same as 0. Maybe a change of 5 or 6 is the same as 0. That's what we're going to test here, is how much of a change really is statistically the same as being 0. So remember, essentially what we're doing is we have a population that we're inferring knowledge about, right? And we're going to take a random sample from that population. There should be an image here if there isn't. All right, we're going to perform some calculations on that sample. We get a sample mean of the change in blood pressure, and we're going to infer that that reflects how much the blood pressure would have changed in the entire population. If everyone took the pill, it probably has something to do with the change that we detect in our sample. That's all review already. Everything we've done this entire semester is just that. That's all we've done. Is that amazing? All that nonsense with t-tests and chi-squares, all just this at the end of the day. Right. Now, remember, if I were to detect, get a sample of people, give them the pill, and I get a change in blood pressure, I'll get a number. I throw those people back in the pool, I get another sample, give them the pill, detect a change in blood pressure, I get another number, and so on and so forth. A billion times I do it, and I plot the change in blood pressure, I'm going to get a frequency distribution that looks like this. This is, again, the central limit theorem. Remember that from the second class? Third, fourth, fifth class, whatever it was. The central limit theorem says if I take that infinite number of samples, the distribution of my delta, of my effect size, is magically normal. Right? And we have a mean. That mean is probably the real change in blood pressure that I can expect from my, my pill. And I have a standard deviation. Remember what that is. Now here's an interesting thing that happens. If, by the way, remember variance is standard deviation squared, right? Sigma squared. That's for review. Okay. If my group size is just 1, let's say I take one person, give a pill, see how much his blood pressure changes, throw him back. Pick another person, give him the pill, see how much blood pressure changes, throw him back, and do that a billion times, I get a distribution of the change in blood pressure that looks like this. If I get two people, give them the pill, change blood pressure, right, throw them back, and so forth, an amazing thing happens. The distribution that I compute actually looks like, oh, my Fitbit just went off. Apparently I thought this was 10 steps. And wait, I'm fit. So two people, my distribution gets tighter, right? So an amazing thing happens. What if I have more people? Well, 5 people, it gets tighter still. So again, I'm taking 5 people, giving them the pill, seeing the change in blood pressure, throwing them back, and doing that a billion times. So the more people I have, the tighter the distribution becomes. That's an amazing thing. Suddenly you start to see that more people is like less variance. It's less width, less error, less fuzziness. Right? So suddenly, oh, maybe I have lots of people. My distribution becomes like a straight line. I know exactly how much the pill is going to change blood pressure. Right? So increasing the sample size is a lot like reducing the variability or the variance of the distribution. So my standard deviation is there, right? The standard error is that. So the standard error, if you recall from third or fourth week, is just the standard deviation divided by the square root of the total number of people in each sample. So as this number increases, the standard error goes down. Right? So more people, less error. It's not a direct relationship, it's like a square root, so I need like a lot more people to have less error. That makes sense. Okay, so increasing the sample size is like reducing the variance. On the other hand, there are other ways to reduce the variance. I could actually get a better sphygmomanometer, a better tool for measuring blood pressure. If I've got one that with all squeeze type, and I read on the dial, I'm going to make some fuzzy errors. If I got like a super digital high-tech one, I get fewer errors. So I can spend money doing that, and that also reduces the variance, or I can get more people in my sample to reduce the variance. So there's a trade-off there. So sometimes there's the cost of the added technology or the added vigilance to reduce the error versus the cost of recruiting more people. There are things we can do, in other words, to also add a lessened error to my approach. It's not always about people. Okay, so remember, let's say the null hypothesis is true, that there is no change in blood pressure, meaningful change. And so if I take a billion samples and I compute the change in blood pressure each one, again, it's going to give a distribution like this, right? Remember, now let's say that in your test study that you finally do, you get your sample of people and you measure the change in blood pressure, and your number is over here somewhere. So this means that the number you got is pretty extreme. It's not typical. The typical one would be under here, right? So it's extreme. How extreme is it? Now, as I mentioned earlier in the semester, if it's so extreme, it has you thinking, maybe it's actually not part of the universe where the null hypothesis is true. Right? So I have to define what that cutoff is for extremeness, such that I can say it's so extreme, it's so unusual that something special is going on. Remember what that cutoff was? What do we call that cutoff? Sorry? Critical point, and that's also what? How do we get it? Sorry? Yeah, you're saying good things. Keep on saying good things. Do you remember? Do you remember? Sorry, what? Alpha, exactly. Alpha is also what? Oh, what else is alpha? It's a type 1 error. All that stuff is true. Absolutely true. Right? So we have a cutoff here, which is the critical region, and everything beyond the cutoff is a rejection region, which means we can reject this null. We say that this probably isn't reality. This is so extreme, it probably isn't real. So that cutoff is determined by alpha. Remember, alpha is the probability of committing a type 1 error. A type 1 error is incorrectly rejecting the null. So we're saying we're willing to accept this probability that we rejected the null in error. Okay, that's again review. We did this already. That's fine. That's the two-tailed test would be 2 cutoffs. Remember that? We divide the region in half. So there's that. So another way to look at it is here's our distribution. If the null hypothesis is true, this is our rejection level. So type 1 error is here. This is the distribution of our null hypothesis. Okay. So if a null is true, the rejection region represents how much type 1 error we're willing to accept. And remember that is denoted by alpha. Now the alternative hypothesis, remember, is probably the type 2 error is denoted by beta rather than alpha. And to talk about type 2 error, we have to talk about the alternative hypothesis. The alternative hypothesis said that blood pressure is changing by a certain amount. We'll determine later on. So let's say we're saying that 10 is what we care about. So the clinicians got together and say a blood pressure change of 10 millimeters of mercury is clinically valuable to us, so that's what we care about. Our alternative hypothesis is that the pill changes blood pressure by at least 10 milligrams of mercury. That's our effect size. Is it big or is it small? I don't know. Depends on what we're measuring. I don't know if that's big or small. I think that's kind of big, actually, in terms of blood pressure. Right? So just as the null has implications, so does the alternative. So let's look at this. This yellow one, is the distribution of my results if the alternative hypothesis is true. All right? And this is the, again, the distribution of my results if the null hypothesis is true. The difference between them, these peaks here, is the effect size, 10 millimeters of mercury. All right. So again, here's my rejection level. This blue stuff is actually the probability of the type 2 error, if this helps to visualize it. Okay. As I increase my type 1 error, I get less type 2 error. Go back and forth, right? As I decrease my type 2 error, I get more type 1 error. That's what I mean when I say there's a trade-off between the two. Cool. Now, we have this thing called power. power is essentially your ability to detect differences, your ability to detect change. Power is defined as really 1 minus the type 2 error, 1 minus beta. There it is. What's beta? Beta is type 2 error. We tend to fix beta at a certain level. Remember we fixed alpha at 0.05? We fix beta at about 80% usually. It varies. Don't have to. We often do. Okay. So a high power means that we're more likely to find things, and a low power means less likely to find things. All right. So here we go. So here is, again, the distribution of our means if the alternative is true, the distribution of the means if the null is true, the difference between them is the effect size, and look what happens now. If I have a bigger effect size, what just happened? I have the same amount of alpha, but now I have less beta. Okay? So before, there was a trade-off between type 1 and type 2 error. To have more of one, I need less of the other. Now I got to have less of both. But to get less of both, I need to accept a bigger effect size. So again, the bigger the effect size, the less error I can have in my study. But that means I can only find big things. So if my pill is only changing blood pressure by 8, I won't find it. Maybe 8's important. You know? So that's a trade-off here. Okay. Bigger still, look at that, it gets really small. Ah, amazing. Okay, how do we maximize power? Yeah, there it is. All right, so the other ways of maximizing power. We can move these things apart, I just showed, or we can increase the sample size. So here's the original sample size. Now we double the sample size. What happened here? Let's look at it again. We double the sample size, we get less type 2 error. All right, we double it again, we get less error as well, and keep on going. So the more people I have in my sample, I can maintain that effect size, the same distance here, but I can shorten the error. That's the power of power. Kind of cool. So now let's talk about how we can use this functionally to compute sample size. So we have some things that are variable here. We have type 1 error, we have type 2 error, we have effect size, all these other things. So let's try to hold some things constant to make your life easy. We're going to hold the type 1 error constant. We're going to hold the type 2 error constant. So we're going to have our alpha stuck at 0.05, we're going to have our beta stuck at 0.8, and that will give the formula a little easier. So suppose the variance in the change in blood pressure is the same for the null and the alternative hypothesis. That's fine. Put that away. So we're going to assume the variances are the same. Suppose we fix the alpha, and we're going to use two-tailed tests only, and we're going to fix the beta at 80%. Now that means all we can talk about now is variance and the effect size. Effect size is delta. All we had to compute how many people to recruit, and we get this formula. So what this says is sigma is the standard deviation of the distribution of that sampling mean, right? Of which version? Remember, there's two curves, the null hypothesis curve and the alternative, they're the same. And this assumption, we just assume they're the same. So we need to know, in the general population, how variable, how messy, how error-filled, how perturbed is the distribution of the thing we're measuring. We also need to know the effect size that you are willing to accept. Is it 10 millimeters of mercury? Is it bigger? Is it smaller? Right? Notice, as this gets bigger, I need less n. As this gets smaller, I need more n. Okay. Let's say I do all this and I get an n of 11.1. How many people do I need? Get? Why? Exactly. I can't have 0.1 of a person. If I go down to 11, I haven't got enough. So the next logical step is 12. So we always go up to the next integer. So here is an example. We have a standard deviation of a change in blood pressure of 7. Okay, so the variance is going to be 49, and we have fixed alpha at 0.05 and beta of 80, and we're looking for a mean change in effect size of 5. So we plug in our numbers, and we get 15.68. We go up to 16. Okay, where did I get this from? In real life, let's say you were designing a study, and you say, oh, we're looking for a change. We can define this. We're looking for a change of 5. We can say that we're going to call these two at 0.05 and 80. But where did I get this number from? Think about a real-life application. Where could it possibly come from? because this is something that represents the characteristic of the pill itself, of the way that the pill is going to be received by the population. How can I possibly know that? It's going to be different for every intervention that I'm testing. How could I possibly know something like this? Well, hopefully, sorry?
You just kind of infer from it.
Yeah, very good. See, so maybe someone else has done something like this. Maybe we have an animal population study. Maybe you go to the literature, maybe someone has a case series, or maybe in your own lab or in your own practice, you have a couple of people who you've given the pill to, and you've got a vague sense of how that works. So yeah, so we need some pilot data. Pilot data tells us what the variance is probably going to be. If we haven't got pilot data, we have animal data. If we haven't got that, I don't know what we do. I think you have to sort of, just throw your arms up in the air and just kind of guess. Right? But you need the variance. You need the width here. So that's part of the fuzziness of all this. So that's how we plug it in. Now, we said that there are two ways of designing this study. We can look at one group, people who got the pill, or we look at two groups, people who get the pill and people who don't get the pill. Right? So again, people who get the pill are the experimental group, people who don't get the pill are the control group, and it's a randomized controlled trial. Okay? So this is the formula for that. Again, we have the same, we set our alpha point of 5 at power 80%. It looks very similar. Notice the difference, two important differences. First is that the coefficient here is 16, not 8. And the second, this is n per group, not n total, n per group. So if you have two groups, you multiply by 2. Okay. Again, so let's look through an example here. So here we have, again, the standard deviation is going to be 7 millimeters per mercury. We're going to fix our alpha point of 5, and et cetera, et cetera. We're looking for an effect size of 5. I plug in the numbers, I get 31.36. I round that up to 32, and then I double it to 64. What some people will do is that they'll double this first, and then they'll round up, and they'll get like 63. Right? And that's not enough. So you round up first, then you double it. Really straightforward stuff. Now, some asshole professor, I'm not saying who, might ask you a question like, hey, you've got 16 people and a variance of 7. What's this, the smallest effect size you can detect? All right, so that's just simply a matter of solving for this. Plug in the numbers here and solve for that. Or I can say you've got an effect size of 5, you've got 16 people, what's obviously the variance of your sample? You solve for that. Who would do such a thing? I have no idea who would ask a question like that. But yeah, I would. So, should be prepared. Okay, so summary. The number of people you need, your required sample size, is going to increase if there's lots of variance. It's going to increase if you have a smaller effect size to determine. It's going to decrease if you accept more error, either type 1 or type 2. And keep in mind that there are different ways of computing sample size. I've shown you one way. Sometimes, if your outcome is dichotomous, like live or die, or pregnant or not pregnant, or that kind of thing, it's a different formula we need. Or maybe we're looking at the time to an event, like a survival time. Different formulas needed. We looked at randomized controlled trials just now. If you're using cohort designs or surveys, etc., a different formula is needed. And also we consider the cost. And maybe it's not possible to recruit a certain number of people, so we're limited again. So these are all variable flowing factors that the statistician has to consider when doing the sample size calculation. Okay, next class, we're going to discuss the final exam. Good times. See you later.